All right, so I'm Jessica Meixner. I am at the Environmental Modeling Center. Today I'm going to talk to you about the Unified Forecast System subseasonal to seasonal application, which uses MOM6. So this is a combined effort of many people from various different centers. All of these people's names should be on the title slides because they've all contributed in one way or another to the success of our UFS S2S system. I particularly would like to thank Brandon, Stephen, Robert Hallberg, Alistair at GFDL for all of their help with MOM6, as well as point out the work of John Day Wing at EMC. So today, our overview of this talk. First, we're going to talk about the motivation about why the Weather Service is looking into this problem, then describe what the Unified Forecast System is, then tell you exactly about our S2S application, and then show a few of our selected results, and then talk about future work. So to get started, right now the Weather Service provides global forecasts both at the weather scale and then at the seasonal. However, with the Weather Act, we have been told by Congress that we will also provide subseasonal and go from weather to seasonal scales, including the subseasonal range. As we are doing this, we have been in the process of updating the atmospheric dynamical core to use the finite cubed sphere grid. So that's been implemented in operations in our global forecast system, but it will also be used in our ensemble forecasting system in the future. And then this is also just a great opportunity to unify and simplify the modeling capabilities across the different scales from regional to global, as well as from time scales from weather to seasonal. So kind of more of what I mean by that unification. So the strategic vision from the Weather Service is up here on the top left is what we call our operational quilt. And this is all of these different little boxes are different operational systems, from the global forecast system to CFS to wave models to regional wave models. And all of these are their own individual systems. But instead of starting with this big, huge quilt of different systems, we're going to move to a way that has a simplification. So we're going to have the unified forecast system and then put together different applications that will go from nowcast all the way up to seasonal forecasting using a simplified model base. And so what we're going to be talking about today is circled in red, so our coupled ensemble, and then our subseasonal going from weather to seasonal. So what exactly is the Unified Forecast System? So the UFS is a community-based coupled Earth system modeling framework. And so it is made up of different components and different models. And then those each have their own authoritative repositories. And then we use this NIMS infrastructure to couple these models together. So the NIMS infrastructure itself is a model driver or a mediator that helps the models talk to each other. The framework that this is built on is NUOPSI, so the National Unified Operation Prediction Capability. So when each of the models have these NUOPSI caps, which then help these models talk to the other models. So for example, MOM6 has the NUOPSI cap in the config source directory, which that's been talked about because it's also used in the new CESM. So We have many different components, and then these are all put together in different ways to create different coupled models. And so we have this overarching system, but then you can have different applications built with different components within this. This is the website for the UFS community page, and they're having a community user workshop at the end of July, which you can find information about there if you're interested in more information about the UFS. So again, we have many different applications. So we talked about unifying our forecast systems. So the first unification is going to be implemented in September of this year, which will be a one-way coupled atmosphere wave system. And then it'll also have a member of atmosphere and aerosols for the global ensemble forecast system. Then there are applications for the coast. So looking at storm surge from hurricanes, there is the hurricane analysis and forecast system. We have an application that just uses MOM6 and SICE5 with a data atmosphere that is used for DA development. And then what we're going to be talking about today, which is our atmospheric model with MOM6, SICE5, and WaveWatch 3, which we're going to be using at the subseasonal to seasonal scales. So our operational target for this S2S system, our first target will be the Global Ensemble Forecasting System, GEFS version 13 in FY 2023. And then that will be followed by a seasonal forecast system implementation, SFS version 1, in FY 2025. So if you think CFS, similar replacement and timescale as that. So what specifically is our S2S model? This is actually the GitHub link, which then pulls in via submodules all of our different components. So first, we have our atmospheric model, which uses the FE3 dynamical core. We use the GFS physics with the GFDL microphysics. We just switched from the IPD physics driver to the Common Community Physics Package driver, CCPP. Our atmospheric model for this application is the C384, which is about 25 kilometers, and it has 64 levels. For the ocean model, we're of course using MOM6. We're using the 1/4 degree tripolar grid with the 75 hybrid levels. We're using the OM4 setup, which we've heard about in one of the previous talks. For the ICE model, we're using SICE5. We're using that same tripolar grid, and we're not using mushy thermodynamics. Our driver is the NIMS, and all the results I will show you today are from the NIMS mediator, but we will soon be transitioning to using the CMIPS mediator, and it just went in to the repository last week. And then one of the other recent additions is we've added the wave model. So we're using WaveWatch 3. We're using right now a 1/2 degree regular lat-long grid, and we're using the ST4 physics package, which is what we're using in operations for the standalone wave models. So this is our current coupled modeled configuration. Right now, most of the results that I will show you today will not include the wave model, but when we do include the wave model right now, we're doing it through direct connectors to the different atmosphere, ocean, and ice components, although eventually it will also go through a mediator. Some of the specific points about this model to note: our atmosphere ice fluxes are computed by SICE. Our atmosphere ocean fluxes are computed by the atmospheric model in the atmospheric model after it receives the sea surface temperature from the ocean. The wave model is two-way coupled to the atmospheric model, so we send the Z0 roughness length from the wave model to the atmospheric model, and then we send Stokes drift from the wave model to the ocean model so that we have sea state dependent linear mixing. So one of the challenges of developing the system is determining the best way for a testing framework for development. And so our current strategy is we develop a prototype, which is a specific instance of our code and the components put together. And then we will run a benchmark, which are 35-day free forecasts, which is our first operational target forecast length. And then we run initialize from the 1st and the 15th of each month from April 2011 through March 2018. So that's 7 years, 168 forecasts. So it's a small enough amount of runs that we can do this multiple times, but it's large enough to give us a statistically good sample size. It also covers both El Nino and La Nina events, and it also covers years of low ice extent. So our goal is to really exercise the model while running, as few as possible cases. So as of today, we have run 4 prototypes. So we call them UFS P1 through P4. And there are code updates and bug fixes as we move along. But the main difference between these 4 cases here are the initial conditions between the first 3, and then the last one, the addition of wave coupling. So for our first prototype that we put together, we initialized everything with CFSR initial conditions. And then for the second one, we greatly improved the ocean initial condition by replacing CFSR temperature and salinity only by actually having a full restart from a CPC 3D VAR analysis that Travis Luca and Yanzhu did from CPC. Then for our third prototype, we also added another product from CPC, their ice analysis, to replace the ice initial condition. And then for prototype 4, in addition to adding in the wave coupling both with the atmosphere and the ocean, our initial conditions for that are just forcing the wave model standalone with CFS and then getting initial conditions from that. So now I'm just going to kind of take you through and highlight some of the progressions and results that we have gotten as we've gone through this process. So our first prototype, one of the big successes of we put all of these components together. There were no tuning of each of the individual components for putting them together, and the whole system worked, and we could stably and reliably produce the entire benchmark. Not only did it work and produce similar scores and performance as CFS v2, we had really great improvement in the ice forecasting skills. One of the reasons that we probably get this is because we did increase, when comparing to CFS, the resolution of the ice model from 1/2 degree to 1/4 degree. So here what we have is the data is in black. The dashed lines are initialized on the 15th, the solid lines on the 1st of the month, and then we have the sea ice extent for the Arctic and the Antarctic. And you can see that you get a huge improvement in the ice extent compared to CFS v2. So that was really exciting, as well as having a stable coupled system. And then when we moved on to our second prototype, that was, again, the major improvement was the initial conditions. So we actually had currents initialized and we were not starting from rest. And so if you, for example, look at the anomaly correlation compared to Ostia for the global tropical SSTs, we had a improvement going from not only CFS v2 to our first prototype, but we saw, again, a large improvement going to our second prototype. So with our subseasonal forecasting system, one of the things that we always look at is our MJO. And both the first and the second prototype, we have increased our skill in the MJO and increased the lead time that is a useful skill to look at. So moving on to our third prototype, the major change there was in our ice initial condition. So we used the CPC ice analysis, and most of the changes and impacts were all in the polar regions, as one would expect with changing the ice initial condition. And we saw improvement in the ice area. So here the black is the data. The second benchmark is in red, and the third prototype is in blue. And again, the dash versus the solid is whether it's initialized from the 1st or the 15th of the month. So with our third prototype that we have, John Day did analysis looking at more specifically at the ocean. So this is showing the sea surface currents for the UFS on the left column and Oscar on the right. This is the combination of all 7 years for January in the first row and April in the second. And then we have for July and October here. So while we do have room for improvement, we're doing a good job so far. Been pleased. So, and then looking closer in, we have the Gulf Stream here. So again, we have January on the top, April on the bottom, and then the UFS on the left column and Oscar on the right. And so, not perfect, but we do get a good representation of the Gulf Stream. And then for July and October, and then we also have the Crocea. So again, these are still the same format. We have UFS on the left, Oscar on the right, and then January, April, and then July and October. So this is kind of our first look at more in depth into non kind of global or tropics skill score and looking more into the detail. So here we have the thermocline at the equator. So comparing the UFS to the EN4 from the UK Met Office. So same format, taking the average of January for the UFS from all 7 years, and then April on the bottom. And you can't really tell much of a difference in these pictures. So we have July and October. So we have the difference. So this is taking UFS minus the EM4 for the 4 months. So January, April, July, and October. So we have a lot of similarities in between the two. So last, what we looked at is the mixed layer depth versus Argo. So again, January and April here, and then July and October. So we don't have the 50-year-long runs that I know some in the previous talks have talked about being a short amount of time. So these are just from the 7 years, but we still seem to have some agreement. So our summary of our results as we have progressed through our prototypes and our benchmarks. For the first one, we had skill that was comparable to our operational CFS models for both the global and CONUS when looking at precip and 2-meter temperatures. Our skill in the ice forecast is significantly better, which is maintained throughout the other prototypes. For the second prototype, again, our atmosphere was similar skill, but we had greatly improved SSTs by the improved initial condition. And then for prototype 2 or 3, our impact is restricted to the polar regions, and we saw improvements of the ice area. So prototype 4 just completed last week, and it's under evaluation, and I would have loved to have shown you results, because our motivation for this is to improve our air-sea interactions, both with the inclusion of passing the Z0 roughness back to the atmosphere, but as well looking at the sea state dependent Langmuir mixing and seeing how that impacts things like the mixed layer depth. So hopefully in the future, we'll be able to show you that as well. So our future work, we're continuing to make new prototypes and development on the model as we work towards our operational implementations. So recent updates, we are looking at comparing the NIMS mediator to the CMIPS mediator as we transition to that. We'll also be adding the WaveWatch model to go through the mediator instead of direct connectors. We'll be transitioning to the SICE-6 ICE model. For the atmospheric model, right now, our land sea masks for the atmospheric model and the ocean model are different, but by allowing for fractional grid in the atmospheric model, we'll be able to have partial land, partial water points for a single atmospheric grid, which will allow us to have conservation, which is very important. And we will also be updating to the latest GFS version 16 physics for the atmosphere, which will also go along with increasing to 127 layers and increasing the model top. All of these results that we have shown have no physics tuning. And so there will also be physics tuning that will go on for all of the model components so that we can get the best forecast of our coupled model. And then we'll also be looking at data assimilation for all of the components, but specifically for our marine components for the MOM6 and SICE-6, which Travis Sluka has a talk later in this series, which will tell you about SOCA and developments in the data assimilation. So I think hopefully finished up right on time and have time for any questions.
Great, thanks, Jessica. I think first up is Gökhan.
Yeah, Jessica, this is Gökhan. Thank you for the talk. I had a quick question. For short time scale prediction skills, such as seasonal time scales, I thought that representation of some climate modes, such as MJO, is quite important. Do you know if you have skill in representing MJO properly so that it would improve the short-term climate prediction skill?
Yeah, so when we look at the MJO, so this is looking at, this is typically what we have been looking at for both the RMM1, RMM2, and then the RMM2. So usually what CPC, the Climate Prediction Center, is looking at is either at the 0.5 or 0.6 anomaly correlation, and they want to see that we're increasing the lead time. And so we have already an improvement from CFS in the future. So the GEFS version 12, which will go in operations in September, they have weeks 3 and 4, and they also are calculating the MJO. And so in the future, we want to be able to match and extend past their capability of predicting the MJO. I can't remember. I can like see the plot in my head, but I don't remember what how far out they were predicting the MJO for the GEFS model, which is atmospheric only, and then they have a 2-layer NSST model.
Thank you very much.
Mm-hmm.
Other questions for Jessica? I had sort of a programmatic, I'll let Alistair go first. Go ahead, Alistair.
Hi, Jessica. Thanks for the talk. A quick question about size 6. So is the motivation for size 6 more than just the physics, or is it just the new physics? So I was thinking about the rheology and whether we can sort of get more of the Cis2 rheology embedded into MOM6 that will help you, but keep the size 6 physics available to you. Do you know whether it's the rheology, the physics, or both that you need?
I think that it's both. I know that there are with the UFS and using community modeling, size 6 is like the supported community model, and so that is one advantage. There's also just the engineering updates between size 5 and size 6, which I know I personally am excited about. But for maintaining using size, it is, from my understanding, the main motivation is the physics. So, yeah.
Okay, thank you.
Okay. Well, I'll ask just sort of a organizational, quasi-philosophical question. I think for CESM, this may be the closest we've been to an operational center in terms of developing a model, you know, that we're sharing in some way. Mm-hmm. And I'm sort of wondering, there's obviously a very big difference between a research model and an operational model, and wondering how agile should we expect your development process to be if say through the EDDI CPT, a wonderful new parameterization of sub-mesoscale or mesoscale processes emerges that really improves a quarter-degree model. What will be your ability to incorporate those sorts of developments, and on what sort of timescales can that happen?
So one of the first things that I think I will point out, so like if we just look at the GEFS system, which is our first operational target. So in September of this year, GEFS will be implemented, and then there will not be a new like kind of major update to GEFS until 2023. So that alone, I think it's not a fast turnaround like it is in a research where you have a new parameterization and you can immediately try it out and make the runs and do this. You also have to make sure that everything runs. You do not want a call at midnight that your model broke and you have to go fix it. So sometimes you want to make sure that it is extremely well tested and well used, but there are opportunities for adding in new features. Some of the models, like the hurricane models, they're updated much more frequently, at least they have in the past. So there's more opportunities for more advancements to come in. But for things like the GEFS model, we're updating right now for 3 years, on a kind of 3-year for the next one. But we also have a moratorium, so because of us switching computers, we're not going to be allowed to. There's kind of a break that you wouldn't normally have.
Okay. All right.
Okay, Jessica, could I follow up on that? Because we understand this 3-year windows and all the issues with going into an operational system. But for many years now, the idea has been to have a system by which the community can try things out with the operational model, not operationally, to try some of these improvements, both in all the components, actually. Now, has that gone by the wayside, or is that still...
No.
Where are we on that? And that's part of this joint work with NOAA and things like that. So where is all that?
I would say that we are very much so in the middle of all of that, in the sense that you can go. So on one of the slides, I have the link to the GitHub repository. That's the UFS S2S model. Anyone could make a pull request to that. Now, there are practical concerns from those in the community that when they want to go and run these models, sometimes there are struggles with it's not compiling on my machine and kind of just technical issues like that. So for the weather model, they've actually made a public release of, they call it the medium range forecast system. And so if you go to the UFS community page, you could find the public release. It has a forum for support. It's known to work on several of the major like exceed machines such as Stampede. So it has been tested and tried there. So all of those things as part of the UFS community and the NOAA NCAR partnership. So we have, we work with Rocky and Mariana and others very frequently and leverage work from both places. So I hope that just continues as we move in the future, and that is the plan and the vision.
Thanks. Any other questions for Jessica or any of the speakers from today?
Yeah, this is Kate Hedstrom. I was wondering, I could download a code from you that runs MOM6 with SICE with the new OPSI caps. I've been trying to run the NCAR system on our machine and it's failing.
So you are more than welcome to try. I think the UFS, I want to say that Denise and others have run the UFS S2S model on Cheyenne. So I think that you could run with an active atmospheric model. I don't see why you couldn't, but I've actually never tried it myself, so I won't guarantee anything.
Thanks.